Learning targets for today. I can factor polynomials with complex factors. And we are going to use our friend synthetic division again today. So just keep it. Well, hey, synthetic division is so much better than long division, and it's better than reverse Sagler. It's really just numbers. Variables go away. All right? So let's keep that in mind. Here we go. The fundamental theorem of algebra states that a polynomial function with degree n, meaning that n is the exponent on the lead term, it's the biggest term. If n is the exponent for the biggest term, how many roots or zeros could that have at most? If n was 3, it would be 3. But in this case, it's n. Yeah, whatever n is, right? If it's a quadratic, meaning x squared is the biggest, is it 2? The most number of zeros or roots it can have? Yeah. If you have a polynomial of degree 5, meaning 5 is the biggest exponent, isn't 5 the most roots it can have? Yeah. So we know this already. Okay? And that means it can have n complex roots. Remember, complex means imaginary numbers in there. If I have a quadratic, all right, and it doesn't touch the x-axis, it really has no real roots. That means it's too imaginary. So at most, whatever that degree is, if it never touches the x-axis, it can have that many imaginary roots. Because remember, it doesn't really touch the x-axis. All right, so we're going to take that and what we already know and kind of apply it to this. This is a big thing here. Linear factorization theorem. If f of x is a polynomial function of degree n, which is bigger than 0, not a negative x, then f of x has precisely n linear factors. That means if it's squared, it has 2 linear factors, like 2 cheeks, basically. If it's cubic, then it has 3 cheeks, and so forth. And we kind of write them like this. If this was a cubic, I mean, I would have 3, right? But what's this a up front? After I get my all my parentheses and factors there, a is the lead coefficient of whatever f of x is. So if I have f of x here, and it ends up being x cubed plus x squared plus x plus 1. Well, I should have 3 linear factors. 1, 2, 3. And the lead term of f of x, that's what we put right here. Okay, so let's say this was 4x cubed. Guess what? I'll put a 4 in front of my linear factors. That's all that means. Yeah, it's a 1. If there's no number, it's a 1. This is really simplifying very complicated math terms. Okay? So you guys know this. It's no surprise. All right? All right, let's begin. Factoring a polynomial with complex zeros. Find all the zeros of this given function f of x. Okay, I'm not going to read it, it's long. And write f of x in linear factorization. That just means factor it with cheeks. Okay. So how do we start? If I asked you to factor that, it would be very difficult. Okay. You need some help to start. All right. Before we were given the factors, and we came up with this, we worked backward. Now we're working actually the opposite way, forward, so to speak. How can I find out what some possible zeros are of this? It's on your notes there. Let's get a picture up. Yeah, it's the graph, it's the polynomial. It's that polynomial right there. Now, look at this. On the bottom it says this is 5 by 5. That's my x-axis. So it goes -5, +5. And the y goes down from -125 to +125. Because if I had it 10 by 10, you would see where it crosses the x-axis. You really want to see the function in all of its. Okay? So, just by looking at that graph, where do you think some zeros might be? So, you're telling me -2 because it crosses right here. Yep. -2. Good. What else? +4, because that's right there. That's -2. So +4. Is there another one? Yeah, right here. It's 1. And if we were to zoom in, those would be zeros. Now, I'm going to pull away from this for a second and show you something to kind of help you understand what we're about to do. if I have the number 100, how do I know that's 2 times 2, which is 4, right? Times 25. How do I know that? Because if I divide all three of these into here separately, it should end up, with no remainder, right? Like 100 divided by 2 gives me 50. Okay, so this goes in, there's no remainder. All right? Yeah, I divide 50 by 2 again, and that's 25. No remainder. I divide 25 by 25 again, and there's no remainder. That's 1. Okay, no remainder. All right? So basically what we're going to do is we're going to take our polynomial and divide our zeros in, and then whatever the answer is, right? So when I divide this in, this is the answer. The next zero, I'm going to divide into what that answer is, and keep on going until I feel it all the way down and I can actually see all of it. Yes. So, I want to show you something. All right? If I have a root that's -2, what's the factor?
+2.
X plus 2. So I put a +2 here, and that's going to go into my polynomial synthetic division. It's the 1, right? 1, -3, -5, +5, -6, and 8. What is the first negative?
Drop the 1.
Drop the 1. We've done this so much. Now what?
Multiply by 2.
And I get 2, and then what?
And subtract.
So what do I get?
You get -5.
-5. Okay, what's the next number that goes up then?
You multiply that by 2.
And what goes here? What goes here? This is -10, and I subtract it, which means...
Add it. So you get +5.
Right, so it's like a +10, so it's going to be a +5. Now what number goes up next?
You multiply it, you got +2.
Yeah, +10, and I subtract it, so what is that?
-1.
-5, so what number goes up next?
-10.
-10, because I subtract that, so what does that equal? Subtract from -10.
You get +4.
I get +4, and what is 2 times 4? 8, and when I subtract 8 from 8, 0. Remember, this is the remainder, right? So now we know this is a root, this is a factor. Done this one, it works. Let's see if 4 works. So if I say x equals 4, what's the factor? X minus 4. So I'm going to put a -4, and check this out, right into here. Remember, I'm going to put into the answer like 100. I divided into 50 next, right? So here's the answer right here, this big old long string of numbers, and I just can go right to there. I don't need to divide into the remainder. That's done. Okay? I don't need to divide into the remainder. That is done. And this whole process is the same thing. Drop the 1. You guys, so I get -4. So what number comes up?
You get -4.
I get -4. Oh, no, that's the answer. All right, handy. I got to step ahead of myself. This is 1, and then I multiply and get a -4. Subtract it. So what do I get?
You get -1.
-1. What number goes up?
+4.
And when I subtract it, what do I get?
A +1.
+1. And what number goes up? -4, and I subtract it, and I get? What was it? -1. I'm multiplying, what's a -1 times a -4? +4 when I subtract. Look at that, 0. Just like with the number 100, all those numbers went in evenly, right? So guess what? This is a 0, this is a factor. Bam! Right. So let's try 1. This is interesting. Let's try 1. If x equals 1, what's the factor? So I'm going to put a -1 in here. And I'm going to go. Now I'm going to wait. I'll wait for you. And being organized is when you run it nice and neat, everything's lined up, it's easier to kind of get through this, okay? Yes, I dropped the 1. -1 times 1 is -1. What happens when I subtract that? You get a +1, and -1 plus 1 is 0. Anything times 0
0.
is 0. And if I subtract that, that's just 1. What goes up next?
You get -1.
Negative 1. And if I subtract that,
You gotta add it to get 0.
0. Guess what? That's my remainder. So that means this is a 0, this is a factor. But here's the kick. How many possible zeros can this polynomial have? Look at this right here. Tell me how many possible zeros it could have. 5. Because the degree, which is the exponent of the biggest term, is 5.
That's where the 1
Yeah, it's the exponent, right. So, yes, because they don't really touch. So, I can't divide in, I don't know what they would be, but guess what? Remember what's left over here? If I were to write this in a polynomial, what would it be? Right. This is 0 x's are here, 1 x is here, and this is x squared. So I have 1 x squared, I have no x's, and then I have a plus 1. Guess what? I can solve that and get my other 2 roots. I can solve that and get my other 2 roots. How do I solve that? I mean, I can't factor it into parentheses, but yeah, it's just 1x squared, so I get the x alone and take the square root, right? So I'll subtract 1 from both sides. I got x squared equals -1. I can't, but you're telling me, in order to realize that, you gotta take the square root of both sides, right? I take the square root of both sides, and first of all, x equals what? What should be written first when I take the square root of both sides? What should be written first before any number? Plus or minus. Oh, that's interesting. That means there would be 2 answers here, right? Well, don't we have 3 here? Plus 2 more would give me my 5. Interesting. So right now I have plus or minus radical -1. Who knows what that is? It's I. Did you hear this?
I said I.
I heard it.
I said I. I swear I said I.
We're the 2 closest people to me in here.
I said
You gotta be loud. What's that? Okay. We will transfer said candy.
I did say that.
Okay. Well, I'm sorry, I didn't hear it. You can be louder and out here. Okay. So x equals plus or minus I. They're imaginary. They don't touch. And what did we say in last class? If I is a root, isn't -I also a root?
Yeah.
Good. Bam, there it is. So, let's summarize. If x equals I and x equals -I, what are the factors here? X minus I, what's the factor here? Plus I. So now, let's write all of our factors together, because that's what they want when they say, write it in its linear factorization. Okay? We have, what's the first one? Those 3 real numbers. In factor form, x plus 2, x minus 4,
X minus 1.
minus 1, and now our 2 imaginaries are
X minus I and X plus I.
There you go. That's it. F of x equals this. Now, these are linear, right? If I were to graph x plus 2, would that be a straight line? That's why they call it linear factorization. So all the factors represent lines. Okay, 3 are real because it crosses the x-axis at these 3 spots. At +1 is a root, at +4, -2. And because it has a degree of 5, and it only touches the x-axis 3 times, 2 of them are imaginary. Positive I and negative I. Holy cow. But what about that A? Remember this little A-hole right here? What is that? Where do I get this A from?
Is that 1?
That's 1.
Yes, it's 1. It's the front right here. When it's not listed, we assume it to be 1. And we don't have to write a 1 there. You really don't have to write a 1 here. Okay, I'm just putting it there so you can connect where it came from. If that would have started with 4x to the 5th, I would have just put a 4 there. And how come I would have to put a... If they started 4x to the 5th, how come I have to put a 4 there? What happens when I multiply these all together? I'm ultimately going to multiply an x times an x times an x times an x times an x. I'll get x to the 5th. But if it started 4x to the 5th, where would the 4 come from? That's why I would have to put the 4 here, so to multiply it to make it 4x. See what I'm saying? Oh yeah, yeah. Otherwise it'd be crazy. So pretty good. Let me get you candy. Right? Taking complex zeros. The complex number z equals 1 minus 2I is a zero of this function here. Okay? Find the remaining zeros of f of x and write it in its linear factorization. Right? So, first things first, if, yes, we are, if 1 minus 2I is a root, what else is a root?
Oh, 1 plus 2I.
Yes, and yes. Bonus for using the proper math term. It's like connection. Okay.
Oh, that's great.
Yeah, it is. It's crazy.
Y'all might start bringing my thank you. So shut up.
Hi! Composites. I'm like, okay, come on, let's go. Factor! I'm like, no, let's go on, let's go on. Okay, so we know these two are zeros. And what are we going to do? If I divide one zero into here, it's going to drop a term and become a cubic. You know, because we always lose a term. Like, look back here. Every time we divided, when we divided the 2 in, we dropped the term. All right, then we divided the -4 in, we dropped the term. Then we divided the 1 in, and eventually, dividing in 3 numbers made our x to the 5th become x squared. Okay? So if we divided these two, our x to the 4th will become x squared, and maybe we can factor at the end. But look what we got to divide into it. Imaginary numbers, not real numbers.
And you got to add 0 because you got 0.
Yes, yes. You want to pay to this. You guys are on point. This is good. I like it. All right. So, I'm going to show you something, and this is what comes into play what you were asking about, you know, adding and subtracting and whatever. There is another way to do synthetic division, and it just requires one minor change. Okay? And I was hesitant to show you, because I like when you know one way, you always do it the one way so there's no confusion. All right? Let's say, in the previous problem, if I had x equals 4, well, I would say, what's the factor of that? -4. So I divide in a -4. I don't know, what was it? 1, -5, I'm not sure. And we would drop the 1, right? We'd multiply and get -4, and then we would subtract, right? Wow. I really don't need to get this. I've just been showing you that way because that's how it starts, and I want you to know one good way and get good at it. But if we have the 0 itself, I can say, well, I'm not going to use this. I'm just going to use a +4. So when I multiply these and get a +4 here, instead of subtracting all these, I just add them. That's it. And how come? Because my -4, I normally subtract it, don't I, when I use this?
Yeah.
Okay, so I can use the 0 and add everything. I still multiply and bring it up. Or I can use a factor and subtract. Why am I showing you this now? Because I don't want you to try and negate this and subtract this. I'd rather have you use this as it is and just add everything. It's going to be a lot easier. Okay, you see what I'm saying? So a little note in your notes, if you use the actual roots, which is the 0, right? You would add when you use synthetic division. If you use your factor, which is in the parenthesis, then you subtract. Okay? So right here, I'm not going to try and ask you, well, you know, put that in factor form. Although at the end we're going to have to, but this is easier to add than subtract. So I know z equals 1 minus 2i. And I'm going to divide that, the 0, not the factor of it, the 0. And I'm going to divide that into a polynomial. It starts with 4. Then as down inside it, there are 0x cubes. You need to represent that 0 in division. I wrote your check for $1 million and I put a 1 on there with no zeros. That's a big difference.
That's $1.
You're going to go, you're going to start spending money, you're like, that's all right, I'm getting $1 million. It must make it $2. You're like, well, then you owe people a lot of money. All right, then I have my 17, my 14, and my 65. Now, now, take your time. We'll line everything up nice, because now we're multiplying in a complex number. Alright? It still works the exact same way. I dropped the 4, right?
Got it.
Now I need to multiply 4 times 1 minus 2i. That's going to give me 4 minus 8i. Okay? So if I have 4 minus 8i, I'm adding. So now there's no keep, change, there's nothing. You know what I'm saying? It's easier. Now, it's just 4 minus 8i. Okay? I got to multiply that times 1 minus 2i. So, yes. Now, this first time, you know how this is a root, so its conjugate 1 plus 2i is? When I do 1 plus 2i next, it's so much easier. Everything kind of just zeroes out. It's crazy. The first one, you just got to get through it. Okay?
Oh, because I is squared.
You got it. You got it. So yeah, 1 minus 2i times 4 minus 8i. And this product is what goes underneath 17. So 1 times 4 is 4. 1 times a negative 8i, negative 8i. 4 times negative 2i is negative 8i again. And then negative 2i times negative 8i is a positive 16i squared. But what is I squared?
Negative 1.
So this becomes negative 1. And what is 16 times negative 1?
Negative 16.
Negative 16. So now I'm just going to combine everything. I got 4 minus 16.
You get negative 12.
And negative 8i and negative 8i.
Or you get negative 16.
This is what's going to go below 17. Okay? Negative 12 minus 16i. Now keep in mind, the only thing you can combine are the non-imaginary numbers. Like I can take 17 minus 12, and that's 5. And then I have the minus 16i. That's how it works. Now, I got to multiply 1 minus 2i times 5 minus 16i. You can see why I gave you a little bit of room here. Oh no, when we get done and it works out right, it makes doing this work not half as bad. It doesn't make it awesome, but it doesn't make it half as bad as it is when you get it completely wrong. So I'm going to go 1 minus 2i times 5 minus 16i. Okay? And we got 1 times 5 is 5. Yep. A negative 16i. A negative 10i. And what is negative 2i times negative 16i?
You get a positive 30.
I squared. And I squared becomes? Which means what is negative 1 times 32? Negative 32. So, I combine 5 minus 32. 27. And then when I combine my middle terms, I got negative 26i. This is what goes underneath the 14. Well, no, this is a positive 5. Positive 5 minus 32. So, no, so see, this is where you got to be careful. Because one minor mistake like that makes the whole thing wrong. And it's like, oh, I did all that work, it stinks. So just be careful, be organized, and it won't be bad. It'll take a little bit more time than normal problems, but hey, if it takes you a little bit more time and you get it right, no big deal. So I'm going to say minus 27 minus, 26i. Negative 27 minus 26i. From that, goes underneath the 14. And what I'll do here is I'll do 65 over so that can get 13. Now, yeah, what do I got?
Negative 13 minus 26.
Now, watch what happens, because you see how this is 1 minus 2i? You see how they're like half or double of each other? And negative 13 and negative 26 are half and double of each other? The middle term is going to end up canceling. So we're not going to have an I, and we're going to end up with just a number. And I've got a feeling it might be negative 65. We'll leave this remainder of 0. Let's try it. All right. 1 minus 2i times negative 13 minus 26i. That's okay. That's okay. What's the first term I get? Negative 13. What's the next term? Negative 26i. Now what happens when I multiply a negative 2i times a negative 13? Look at that. Those cancel. And then what's a negative 2i times a negative 26i? 52i squared. What's I squared? And what's 52 times negative I? Or excuse me, times negative 1? It's negative 52. Now what happens? These two cancel in the middle. What is negative 13 and negative 52? Holy smokes. And I'm adding this. Yeah, you see how if you just work it? 0, that's a remainder. This works. That was a lot of work to find out if that's a root. This next one, you're going to see how much more simpler this becomes. Okay? No, it's not going to be half as much. Yeah, this would be a longer.
I need like 20 minutes.
On the final for the district, I have yet to see one like this. Okay, so this is just work using your algebra work, and this is something that's going to be stressed too much. But let's do this. If 1 minus 2i is a factor, then 1 plus 2i is a factor. That's going to go into here. Watch what happens. No. Watch what happens. You ready? I'm going to drop the 4. What is 4 times 1 plus 2i? Stop it. It's 4 plus 8i. And don't forget, I'm adding, right? Because it's the 0. What's 4 plus 4? 8. What is negative 8i and positive 8i? You see what I'm saying? What is 8 times 1 plus 2i? 8 plus 16. The i's cancel. And don't forget, I'm adding this, right? What's 8 plus 5? Now look what my next lead term is. 13. It's negative. So what do you think is going to happen? See what I'm saying? Yeah. What is 13 times 1 plus 2i? And I'm adding, so guess what? Cancel, 0. Look how nice that is. Listen, I told you, once you get past the first one, the second one is so much easier. It's just that first one. You got to grind through it. So now, guess what? Bang, that works because that's a 0 remainder. Now, what do I have left in polynomial form? Real numbers. Yeah, well, what?
So 13.
I'm going to find those zeros by factoring. All right, I'm going to find those zeros by factoring. Remember the rest. All right, so now we have this quadratic and we need to try and factor. If I do slip and slide, it will not be factorable. Meaning, if I try and factor it this way, I move the 4 out back here, I multiply this times 4, right? I get x squared plus 8x plus 42 equals 0. If I cannot factor that, but if I can factor it, I can continue and I'll get 2 factors. If I can't factor that, which I can't, that means I need to use the quadratic equation. The quadratic equation is, who remembers it? X equals negative b plus minus
2ac.
No.
4ac.
4ac is here, but you're missing something.
B squared.
Oh, yeah.
Minus
All over 2a. I mean, it's not bad to just plug the numbers in, but then we got to simplify. Okay? So, if my a is 4, my b is 8, and my c is 13. Right? And we're just going to plug and chug right now, okay? So, I have a negative b. So, b is 8, but I got to negate my 8. Plus or minus the square root of my 8 squared minus 4 times a, which is 4,
C is 13
times c, which is 13,
over 2 times
all over 2 times 4. Now, wow. Let's clean this up. In your calculator, tell me what you get. Forget the square root. Just put an 8 squared minus 4 times 4 times 13. So I'm going to
That's minus 4.
That's minus 4 times 4 times 2. Yeah. We'll have to listen back and see. All right, what do you get? I know I got an equal sign there. Tell me.
Can you parentheses?
However you put it in the calculator. 64 minus 16 times 13. Negative 144?
Yeah.
So, negative 144. That's what you're telling me.
Yes.
All over 8. What's the square root of 144? It's 12. But guess what? Radical negative 144 is the same thing as saying radical negative 1 times radical 144. So that is 12 times, what's radical negative 1 again? That's 12. So, you know what, an easy way to do that? Whenever you see a negative, just take it right out, and it becomes I. Times radical 144. Yeah, so that's 12 times I, which is 12I. So I'm going to rewrite this as negative 8 plus or minus 12I all over 8. Wow! Is there a common factor between 8 and 12? 4. So I can take a 4 out of all those. Right? 4, yeah, goes in here twice. 4 goes into 12 3 times. And 4 goes into 8 twice. So if I really wanted to get really crazy with it, yeah, I've got negative 2 plus or minus 3I all over 2. I can rewrite that as negative 2 over 2 plus or minus 3I over 2. And why would I do that? Because this becomes negative 1. So there are two answers there. Negative 1 plus 3I over 2 and negative 1 minus 3I over 2. Which means, question, are these imaginary?
Yes.
Yeah, there's an I in there. Were our first two roots imaginary?
Yes.
So if I graph this, will it touch the x-axis at all?
No.
Should we check it?
No.
You guys are comical. All right, first let's write it in its linear factorization. Okay, so hold on. Let's list our roots. Our roots are 1 minus 2I, 1 plus 2I, negative 1 plus 3I over 2, negative 1 minus 3I over 2. Now, these are all parentheses like this, right?
How come it's not?
No, they don't. They don't. They're all imaginary. So if I'm going to write this, all right, in factor form, this is x what?
Oh, it's x plus 1.
This is positive up here, isn't it? So it's minus 1 minus 2I. Okay? So what would this one be? X. There is a plus up here. I mean, I could distribute that negative if I want, but why? What's this next one? Don't forget, this is plus out here, right? So it's x minus negative 1 plus 3I over 2. And this one here is x minus negative 1 minus 3I over 2. Am I done? Is this my f of x? Why am I not done?
We gotta add the 4 first.
Yes, thank you very much. Remember our a that goes here? If I multiply these all together, my first term would be 4x, or excuse me, will be x to the 4th, because I'm multiplying x by itself 4 times, but doesn't it need to be 4x to the 4th? So I got to make sure I put my 4 right there, and that's my answer. Holy poopsicle. That's a lot. That was a lot of work. If you can get to something like that, that's great. There's the bell. Have a good day. I think tomorrow, I'm going to have books in the back. When I say tomorrow, Monday, I will not be here. So